Hello to this video, and hello was also the salutation that Google Gemini used to greet me. In this video I would like to test Claude of Anthropic, and it's greeting me with "Good afternoon, Matthias." I would like to test now how this large language model performs in solving our last and first and only online assessment in electrical engineering, in the electrical engineering model. In a former video, I have solved it by myself by hand, and I got this more or less impressive score of all answers correct. But of course, I've also developed the questions some time ago, so I more or less know, and as a teacher in electrical engineering, I should know how to solve these tasks. So the question is how Claude of Anthropic will perform in doing so. So I've just logged in. There's some message here that they temporarily switched to Haiku and Concise, which are, I think, the not so powerful models of them, because the Sonnet or Sonnet is currently unavailable on the free plan. I don't have a paid license with Claude. But okay, so I will click away this message here. Last time I used this, it stopped doing or performing after I think 15 or so questions, because then I had too many prompts on that day. So we will see how many questions we can get solved with this today. So I will submit my solution, my trial by hand. You can have a brief look at some of the questions already and go down and say, Neue Vorschau beginnen. I would like to have a new trial. And as a student, you would have 19 minutes to solve this online assessment. And there's some message that it currently should be blocked, but as a manager in the course, of course, I can overwrite this message. So first question is, we have a diode, we have a forward voltage, we have a source voltage, there's some funny trailing resistor, some series resistor. So this term here was just chosen to confuse large language models like this. So we will see what Claude does of this. So, and the question is, how large must this resistor be? So from the difference of the two voltages, we can calculate the voltage across the resistor, and this divided by the current should give the resistance 0.75 kilo ohm. Does not sound too bad. I need to convert the decimal dot into a comma and check the result. And okay, that's correct. So next question. And this one is one with a circuit schematic, and the circuit schematic is drawn in a way that it should also confuse large language models, because it maybe looks like a parallel connection of the resistor and the inductor, but as you can see, it's a series connection. So let's see if it works. If I copy this and paste it into Claude and upload and ask him, kannst du bitte, oh, can you please solve this task for me? And I will copy this here into this window so I can always copy and paste it from there. So we have a resistor and an inductor. We have the real power that is dissipated here in the resistor. We have the active power that is dissipated in the inductor. We know the source voltage and the frequency, and now the question is, how large is the inductance? Okay, and it calculates it pretty quickly. Says we have some active power, we have some reactive power, and the inductance can be calculated using this formula. L is Q divided by 2 times P times F. I would not really agree on this, because this is volt ampere reactive, or volt multiplied with ampere. If we divide by frequency, we multiply by seconds. So the unit that we get here is volt ampere second, but we should get volt seconds divided by ampere. So in this equation here, the Q is not the reactive power, it's the reactance. So I assume this value here has the right range, the right order of magnitude, but still I think it's wrong. So let's check. Yeah, and it's something else. So no, it would have the right order of magnitude if it would be in Henry, but in millihenry it's just way too small. Okay, so that's unfortunately not correct. So we continue with the next question. The next question is a longer one, so I probably need to zoom out a bit to make this fit on the screen here. We do nodal voltage analysis. The circuit is also drawn in a way in this rather unusual triangular shape to confuse large language models, because you will seldomly see something in a textbook or in other task sheets. There you usually have right angles, not 60-degree angles. But still we have two nodes. This is the reference node. We have node 1, node 2 can calculate two nodal voltages from this system of equations here. And the question is, what is the entry there? And so let's copy this and open up a new chat, paste it there, and once again ask, can you please solve this task for me? And so I11 is the sum of the current sources at this node. So it should be this current source minus this current source. So 1.8 minus 2.1 should be minus 0.3. So to find the value entry in the column vector of the source currents, I will repeat this equation and plugging this in. It tells us it calculates some nodal voltage. Yeah, and that's not correct. I mean, this is maybe the solution of the system of equations, but even the system of equations is not correct. Not correctly set up. So this is certainly wrong. The correct answer should be minus 0.3, as you can see. Okay, so overall, not a very good start for Claude. Then let's see if I can go back to this task here. Because here we already had the schematic and we ask what is the effective value or RMS value of the voltage drop across the resistor. And this voltage we would like to have in volts. So to find the voltage drop, we can use the power. That's a good idea. And reformulate this equation. But the problem is we don't know the resistance yet. Okay, so I could ask back, is there a way to find the resistance from the given values? Because this is not some satisfactory answer. Okay, and so now it does something. Okay, therefore the resistance of the load is 130 ohms, because now it assumed that the full voltage is across the resistor. And so now if we ask back, what is then the voltage drop across the resistor, then it should give back it's 171 volts. And this is certainly wrong, because this is the full voltage. Voltage across the resistor is something less. Okay. ChatGPT and Gemini were much stronger. Anyhow, we continue. What is the power factor of this load? This is a simple task, because the right approach is given here, real power divided by apparent power, and right calculation of the apparent power, 0.95 also makes sense. And it's unfortunately something else that is very close to this, but I don't know. So this calculation here, I think this approach is correct. I think I somewhere have Octave here still open with some similar calculations. So if we would do 224 divided by the square root of 224 squared plus 63 squared, we get this right answer. So this answer, the approach is right, but the number crunching is wrong. So sad. Okay, next page. We get back to the diet equation. This was this prompt here. And ask what is the electrical power that is dissipated in this trailing resistor. And it says the power is current squared times resistance. And so we get 8.8 milliwatt. And this could be right, but it isn't, interestingly. Why it isn't. So we have the current there. The resistance that we calculated before was correct. So if I go back to Octave and do this thing, so 11 milli squared times this resistance, which was 754.55 current squared times resistance is 91.3, and not this. Interesting. I mean, this is correct. This is not correct. What can go wrong in a simple calculation like this? How do you end up with, I think maybe what it did is just 0.011 multiplied with 700 this. So then you don't end up with 8.8, but you end up with 8.2. So I'm not sure what is wrong here. Okay. It's not too good for Claude until now. So we have a new circuit. Also, these two resistors, or this circuit, is drawn in a way to confuse large language models. It looks like a series connection, but you can see because of the nodes, current splits up. It's a parallel connection with the same voltage drop across the resistors. And now the question is, the following interconnection of two resistors and so on is supplied at the terminals. I have to open up a new window and once again ask, can you please solve this task for me? So to do this, we need to calculate the power dissipated in the resistor, current squared times resistance. So the resistors are this and that. And yeah, the current is the total current. So at first we would need to calculate the current in each branch of the circuit using, for example, a current divider rule. This does not happen here. So yeah, this is certainly wrong. This would be the value if the full current, if we would have a series connection, if the full current would go through both of the resistors. So this here should be something smaller. Yeah, but I don't know. Once again, maybe this calculation here is wrong. Okay, so Claude is not in the best condition today. So we go back to the nodal voltage analysis task, which was this one here, and can ask a second question. What is the value of the entry G12 in the nodal conductance matrix? And this should be given in millisiemens. And it says this is 0. And this is wrong because it should be 1 over R2 with a minus, because this is the coupling conductance between these two nodes. Okay, So the right answer is this, not 0. Then we go back to this question here with the inductance and so on. But here I had the slightly different circuit. So I will copy this here once again to some new chat window and say in an ohmic inductive load and so on. We have this and this. And the question is, how large is the phase angle of the complex impedance? And let's see what it does. So it says the complex impedance of the load, we need to have Q for the reactive power, P for the active power, and do the arcus tangens of this. The inverse tangent, and this makes sense. This is the right approach. And 15.6 could also be, if the reactive power is much smaller than the active power, could be the case. And this is the right answer. Okay. So then we go back to what we had before, the power dissipation in a resistor. This was this circuit here exactly. And ask, what is the total power that is dissipated in both resistors R1 and R2 of the circuit? And the total power can be calculated from the sum of the individual powers. And the first power already was calculated, but it was wrong. The second power can be calculated the very same way, but it will be also wrong. And then the total power is this. So let's see what we get here. And check. And this is also not correct. This is also higher. Okay. So then I think this circuit we did not hit before. So I will once again open up a new chat, copy this schematic, which also looks like a series connection, but if you carefully check, it's also a parallel connection. And so here the current flowing through the first resistor is looked for. So Claude says the circuit has two resistors and the circuit is supplied by a current source. Okay, and we can use Ohm's law, and V is the voltage drop. And okay, and now this is some interesting argumentation or some instrument reasoning. We say, okay, if we want to have the current, we need to find the voltage, and to find the voltage, we take the current and calculate the voltage drop, and from this voltage drop back again, we calculate the current, and oh, we got the same current that we started with. But this, of course, in this sense, does not make too much sense. Yeah, so this is wrong. It must be less than this because the current splits up. Okay, so Claude is not useful here. So we go back to this schematic. Yes, and ask what apparent power that corresponds to the magnitude of the complex apparent power is dissipated in a load, and this should be specified in the unit volt ampere. So we get 244. This is reasonable. This is this squared plus this squared and then the square root of this. Like this calculation can be, of course, that the calculation is wrong. And it is. So this is really interesting. If I go back to my Octave window and just check this term here that we already calculated. Yeah, it is 232.7 as also mentioned here, and not this what we had before. I don't know why, but something horribly fails here. Okay. So next page. looks like this, that we are back with the nodal voltage analysis task, and this was this one here. And now the question is, what is the value of the entry G22 in the nodal conductance matrix? And it's calculating and calculating, and it says it's 0.36 millisiemens, and this is way, way too small because we have some resistances in ohm, and so we get some conductances in Siemens and then some or fraction of a Siemens, but we should get something a couple of hundred millisiemens. So already the order of magnitude here is wrong. The value is also wrong. It's somehow wrong. Okay. So next question is back with the diode. And here it's asked for what is the electrical power PD that is dissipated in a diode. I think this was before. The approach was not too bad. The result was wrong. The approach here looks correct, and I think this could be correct. Yeah, 3 volts times 11 milliampere gives 33 milliwatt. And we check, and that's right. Okay. So the third point for Claude here. Still not very good. Not very meaningful. Next question is once again related to the matrix equation and the nodal voltage analysis. So what is the entry G11 in the nodal conductance matrix? And this result here also just by the order of magnitude must be wrong. And it is. Does not make any sense at all. Okay, so then we have this circuit. I don't know if we had this one already. So this must be one. This circuit here. No, it's not this one. Complex impedance. I think this was also something else. And then, no, I think we don't have this one yet. So let's copy and paste this into a new prompt and copy the task once again. And also these two resistors look like they are in series, but they are in parallel. Here it's calculated like a series connection. This parallel connection is not recognized. So the result here is certainly wrong. And yeah, the total resistance is smaller. Okay, so same question here. What is the voltage drop across the circuit? And it's calculating it in a way as it would be a series circuit, which is wrong. So this result is also wrong. It's much less voltage or much smaller voltage. Then we go back to this diode equation or calculation. This was the trailing, so-called trailing resistance task here. What is the efficiency eta of the circuit? Assuming that all electrical power in the diode is converted into visible light. So we need to have the total input power, the power of the resistor, plus the power that is dissipated in the diode. But this result was unfortunately wrong. This was right, so this is also wrong, and that's why the efficiency is way too high. Should be just 20%, something like this. Okay. So then we can go back to, I think this was this task here exactly. What power is dissipated in the resistor, in the second resistor R2 of the circuit? And I think it had, it had already calculated this before, but the result was wrong. And now it tells me you're out of free messages. Yeah, so this is wrong. Okay, and so now Claude stops me from solving our electrical engineering online assessment here because I'm out of free messages until 7 p.m., which is too sad.